You can see my slides still, is that right?
Yeah, perfect.
Brilliant. So I'm going to give you a quick talk of the current and future efforts related to metal-cooled reactors in the UK. And I'll start here. Liquid metal reactors, dominantly looked at in the UK, we're focused on lead and sodium. There's also lead bismuth, eutectic, but we're not considering those for a few reasons. Go into those details if necessary later on. There are some key differences between the two coolants. Lead got a slightly higher melting point, which causes problems in terms of plant operation. But it's also got an extraordinary boiling point, giving it an extreme envelope for operation. Sodium got a very low melting point, meaning that plant operation is it's relatively easy in terms of getting things started and shutting down and so on. But the boiling point is low, and that potentially limits some of its applications in terms of cogeneration and the things that we've been speaking about earlier from Robin, Michael, and the team. Neither of these reaction with water is very different between the two liquid metals, and reaction with air also, and the density is also very different. Lead fast reactors are very dense. They're very heavy. You're talking, 11.3 grams per centimeter cube. That's on the order of what UO2 is. That's more than UO2, and therefore you get things like buoyancy problems and things like that. So it's not trivial. Whereas sodium around about the same as water in its density. So there's some big differences, but they share some challenges and some benefits. To both of them, there is benefits, and these are fast reactors. There aren't many fast reactors there aren't many other fast reactor types that we can say have got operational experience. In fact, there are very few. We've obviously done a lot of work in Europe and the West on sodium fast reactors, but they have been used. Lead fast reactors have been used, and Paolo went into this before, quite successfully over in the Soviet Union, former Soviet Union, and we know how they perform. We know the problems with them, and we have suitable materials for first of a kinds. As I mentioned before, with both of them, we've got a very high margin to boiling and walk-away safety in both of them, similar to the very high temperature gas reactors. Gas reactors probably sort of hold the baton for best at that. But this is, as Susan said earlier, sometimes you've got to choose the best of all options and so on. But yeah, anyway, let's move on. Vessel operates at atmospheric pressure. This is good. You don't have things like major incidents when you've got loss of coolant accidents. And of course, they can be very compact. These reactors can be extremely small and high density power. We were looking at before in phase one, I was working with Tim and a few others on the lead cold reactor. And that was a tiny reactor, and we'll go into the sizes later. But it was incredible. The problem with that was the density. It was very difficult to move around with lead in and things like that. So, but lead's inert, and one of the major benefits, and I've said this before, is fast reactors, and so its capability to accommodate both open and closed fuel cycles. The drawbacks. The one that Nick drew upon earlier is that it's opaque, and this causes an immense amount of problems in terms of sort of seeing fuel failures, seeing what's going on inside your reactor. But technology has taken that up, and we're now using. There are some extraordinary advances that have been made to ensure safety there. Corrosion rates are very dependent on impurity content, but that's the same in most reactors. Freezing of coolant, as I've mentioned, is an issue, especially with the lead fast reactor. We need to maintain temperatures above the melting point to ensure that you're not mucking up the reactor internals and things like that. Mentioned its density, and mentioned sodium is very reactive with water and concrete, air and concrete and fuel. Mentioned earlier. Most of these issues are surmountable with innovation. Some of them need to be designed away or designed to be less severe. But overall, there is no major drawbacks, and there's innovation has been sort of pushed on. And this is why that represents these liquid metal reactors were represented in the AMR phase 1 concepts. 3 different ones were put forward: 1 sodium fast reactor and 2 lead fast reactor concepts, next to the high temperature gas reactors, molten salt reactor, and tokamak energy fusion reactor. All of these aimed to generate low cost electricity, increase flexibility in delivering electricity to the grid, and cogen and things like that. As Paolo said, Westinghouse were very deliberate in their choice of a lead-fast reactor to go at these aims. This was not a mistake, and this was shunning thoughts from the past. And the choice of choosing the choice of a lead-fast reactor was very deliberate. The 3 metal-cooled concepts that were in phase 1 were all quite different. There was a small, medium, and large. The small one, as I mentioned before, was the lead cold reactor. You've got a nice picture there on the left. It's 55 megawatts electric. It's very cheap per unit, targeted. It was fueled for life, so 25 years fueling, and it was modular build and transportable. The idea was to build in the factory 10 or so per year. Then if you go over to the right-hand side, you've got the arc reactor, which is still being pursued over in Canada. It's slightly larger, so 100 megawatt electric, and it's fueled for 20 years, and it can be refueled. It's got a design life of 60 years, so three lots of fuel, and that's that. It's metal fuel as well. So there's a slight change. The lead cold reactor was initially fueled with UO2, the arc reactor metal fuel, and Westinghouse in the middle. It was chosen because of its competitive levelized cost of electricity, LCOE. It's got a 10 to 20 year fuel cycle, so it's refuelable, and it builds off the back of AP1000 development and things like that. So it on paper it was deliverable, and that's why it was chosen to go to phase 2 of the AMR program. And yeah, it's just worth noting that all of these had walkaway safety, relatively small footprint, and evolutions of previous plant, or relative evolutions of previous plant. Nick this from Nick, who just presented it, but it was just a point. So the UK is in Gen 4, the Gen 4 forum, the GIF forum, and in it we are looking at not only VHTRs but sodium-cooled fast reactors, building up of the experience that we heard about earlier today, up at Dounreay, and so on. And yeah, this is an international consortium. If you liken this to the GIF to the fusion world, this is the ITER project, and you know, everyone's digging in to make advances, and with that comes politics and things like that, I expect. But I leave that to the likes of Nick and Susan and the NNL to worry about. There is a huge net that's being cast in the UK to support this, and yeah, you can see all of the various academic and industrial and national labs over the screen. So that's the UK's involvement in SFRs. I just wanted to talk a little bit more about the Westinghouse LFR and what does it enable within the UK. So high temperatures up to 650 in its later phases. So this is not as high temperature as the VHTR, but it still enables some of those lovely cogen things that were spoken about. The levelized cost of electricity is on par with other low carbon technologies and aids the net zero 2050 aim. So we're talking, you know, it's a big reactor. It's not a very small SMR. It's quite a large reactor, you know, 500 or so megawatt electric. Therefore, it can make quite a big dent in the UK's net zero aims. It's a fast reactor, as mentioned before. It means that we've got the option to close the fuel cycle. And fast reactor fuel, as Lindsay actually said in the chat earlier, Springfields has the ability to produce fuel at 100% enrichment, which means, and not many countries around the world have that ability. So the UK is rather well placed to produce fast reactor fuel. Even if we don't build fast reactors, which I hope we do, we should be delivering fast reactor fuel around the world from the UK. And yeah, that's that. There's also lead's not a one-trick pony. So molten lead's being used, being considered for use in fusion energy as well. So the facilities that we build up in the UK devoted to lead will also support, may support fusion reactor work as well. So in fusion reactors, lead is used as a potential breeding material, lead-lithium breeding material, or it's used as a boring old coolant material. So there's that. And in doing so, we're developing, as we develop materials for lead-fast reactors, we're also potentially developing materials for fusion as well, and sharing materials and standards, and sharing test facilities and potential neutron sources and neutron test facilities as well. So I think that's an interesting thing to note for lead. And of course, the same could be said as well for other metal coolants as well. A quick note on some issues with lead and some things that we're working on here in the UK. One of the big problems that I mentioned before is lead is quite susceptible to initiate corrosion if you don't control the oxygen content too well. The graph I've shown here is oxygen content on the x-axis. You start off on the left with low oxygen content, and as you go and increase your oxygen content, you vary the behavior. So corrosion at low oxygen contents is very high in these steels that are considered, and this is because the low oxygen content lead means that there's no protective oxide, and you're effectively liquid metal corrosion is occurring. On the other side, you've got oxidation occurring. So you've got too much oxygen in your lead. You start oxidizing your material, and that causes problems as well. And that was this oxygen control was one of the major issues that contributed to the accidents or the incidents with the Alpha class submarine reactors. And controlling that is really important. And we're developing new materials that have got larger transition zones and lower oxidation rates, things like alumina forming steels and things like that. And we are testing them as an international effort going on to test these materials. People like the Swedes, people like Italy, and so on are all looking at these new materials, and Germany too. Here in the UK, we're collaborating with some of them, and at Bangor, we're doing that. We've got a couple of projects underway with the National Nuclear Laboratory as part of the FCP program. That's to look at corrosion rates in static lead, and Nick and me have been scratching our heads trying to make this happen over the last few months, and we've finally got some data, which is brilliant. And we've also got a really exciting project with Westinghouse and the NNL on creating a lead loop erosion testing facility called Bullet. ANEA down in Italy have a similar sister facility already, and this is what we're basing our design upon. Ours is going to be also able to do some static lead testing in there. So in the storage vessel, we can do some static lead testing too. And this is to look at alumina forming steels, is to look at fuels, is to look at everything you can think of, really. We're quite excited to get it going. Hopefully this year, I should say. Testing and flowing lead is going to be quite exciting. So going up to 4 meters per second in lead, looking at pump impeller materials and things like that are all very important. They don't beat the real thing. And Paolo said earlier, there are some larger facilities that are part of the AMR Phase 2 project led by Westinghouse that are going in around the country at Wolverhampton and other places like that, which we will contribute towards. And it's lovely to be in this kind of very purposeful program. Tim and a few others have mentioned fuels before, and the fuels for these lead fast reactors and the sodium fast reactors exist. We saw some lovely PIE of some annular fuel for the for the PFR earlier, and wasn't that great. We're also looking at some advanced fuels. There's some benefits of going to higher density uranium fuels, so looking at uranium nitride and potentially uranium borides as well. Uranium alloys are in there. We're doing some work here at Bangor, and we're doing some work with the NNL and in collaboration with the University of Manchester as well on looking at these advanced fuels. So the pictures on the right, you can see some work that we've been doing with KTH over in Sweden on a uranium nitride, UO2 composite fuel. And at the bottom there, you can see a diboride kernel that we manufactured at Bangor. I think it was last week. I'll have to ask Phyllis about that. But I thought, yeah, we're making progress of, kernel manufacture in a new scalable route in the UK. And that's with the NNL. And it's quite fun. So in summary, the UK is currently bringing academia, industry and national labs together to develop both lead sodium fast reactor technology. It's a real international effort, and it's working with people like GIF. It's working with consortia led by Westinghouse, and it's quite exciting times. We've got major benefits, and we've spoken about those in terms of cogen and the ability to load balance on the grid and things like that. We've got a background in metal fast reactors. We know some of their key problems. We know some of the materials to use with them. So we're building off a solid base, even though it's shrinking into the past. We've got people like Russia who are pushing and developing and building a lead fast reactor as we speak, as Paolo mentioned earlier. There's benefits for UK grid, and we are actually building physical hardware in the UK right now to support us going forward. And I think that's a really good base to propel us further. I've got some questions for the conversation later, and I probably can bring these up later. But yeah, that's the end of my talk, and thanks for listening.
Thank you, Simon. Yeah, it's good to see that sort of fission fusion overlap, and maybe that's something we should talk about a bit more in the discussion too. Anyway, we better move on.